All right, okay, it's on now. Hello, everybody. My name is Ning. I'm a graphics developer working for Unity on real-time ray tracing. And today I'm going to be talking to you about DirectX ray tracing in Unity 2019.3. Hopefully after this presentation, you'll have enough background to start working with it on your own. So just to start with, I wanted to ask, how many of you all have developed in Unity before? And how many of you have worked with the high definition render pipeline? Okay, a lot of overlap in those groups. So I'll try to go into a little bit more detail for the people that haven't developed in Unity before, and of course there'll be time for questions afterwards. Okay, so I'll start with an introduction into DirectX ray tracing and its integration with Unity, and the second part of it will be really quickly going over the HDRP features for ray tracing. As many of you may have heard, DirectX ray tracing is a DirectX 12 feature designed to leverage the hardware acceleration that some GPUs provide for ray tracing. For real-time rendering, we generally ray trace as a complement to rasterization rather than a replacement. For example, when rendering reflections that capture faces that are obscured from the camera view, or refractions, once again capturing things that we can't see straight on from the camera. We can also use ray tracing as a replacement for compute shaders in algorithms that call for raycasting, like global illumination, participating media, or caustics. So to start with, I want to go over two major concepts: ray tracing acceleration structures, which define what we're going to be drawing, and ray tracing shaders, which defines how we're going to draw those things. So the ray tracing acceleration structure captures the scene we want to render in 3D space. This is the data structure against which we cast all our rays, illustrated on the right here for the Cornell box shown on the left. First, we begin by defining one bottom-level acceleration structure for each unique mesh, in this case a sphere, a prism, and a plane. In the next level up in this diagram, the instances are constructed by associating a transform with a material and a pointer to one of those bottom-level acceleration structures. Then these instances are grouped together in a bounding volume hierarchy by the driver to create the top-level acceleration structure. This is exposed in Unity 19.3 through the ray tracing acceleration structure class. When creating your ray tracing acceleration structure, you can choose that it's managed either manually or automatically. If you're managing it automatically, then game objects will be added to the acceleration structure as they're created or added to your scene. If you're managing it manually, on the other hand, you have to explicitly add it in your C# script by calling the add instance API, and then once per frame, you want to call the update instance transform API on any game objects that you're going to be moving. In either case, you can specify a layer mask when you're creating your acceleration structure in order to filter out which layer the acceleration structure is actually capable of grabbing game objects from. So in addition to that, for both manually and automatically managed acceleration structures, you need to call this build ray tracing acceleration structure API once a frame. And what that does is it goes through and checks all the transforms and to see which ones have changed. And based on that, it either rebuilds or updates the acceleration structure on the GPU as necessary. So aside from layer masks, game objects are also filtered based on ray tracing mode, which is a new setting that's been added to the renderer. Ray tracing mode tells the acceleration structure how frequently a game object will be updated and in what way. If ray tracing mode is off, it won't be ray traced at all. If ray tracing mode is static, then we expect that game object to stay in place the whole time. For a dynamic transform, we expect that the transform may be updated, but that the geometry will stay the same. Whereas for dynamic geometry, you can update both the transform and the vertex and index buffers associated with that mesh. So currently, only static and dynamic transform is updated in Unity, but dynamic geometry is next on our list. So next, I want to go over ray tracing shaders, and I find it helpful to group them in two major categories based on their usage in Unity: ray trace and surface shaders. Ray trace shaders are generally defined in a .raytrace file that you then call dispatch on, much like compute shaders. In these shaders, you'll find the raygen shader, which is the first shader that gets executed on dispatch of the shader. And usually there's also a miss shader, which is the shader that gets executed if a ray fails to intersect with anything in the acceleration structure. Surface shaders, on the other hand, are defined in shaders, which are used in materials that are applied to objects in your scene. So in these shaders, you'll want to add a pass for your closest hit shader, which is the shader that executes on the hit that's closest to your ray origin, and an any hit shader, which is a shader that executes on every single intersection. There's also support for callable shaders, which are just function callbacks in shader form. I also want to point out that DXR groups closest hit and any hit shaders together in hit groups, just for your information on DirectX ray tracing. So to illustrate these shaders in action, we start with the raygen shader. And in this case, we have a raygen shader that shoots all the rays out from the camera. But as we'll see later, you can generate those rays however you want. So the first ray on the leftmost side here misses any geometry in the scene, so it just executes a miss shader. Next, the second ray down intersects with two objects, one of which is occluded by the other, both of which have a closest hit shader. So in this case, even if the ray intersects with the occluded cylinder first, the closest hit shader on it doesn't get executed. And the reason for that is that closest hit shaders only get executed after we've finished going through the entire acceleration structure. So we've already found out that there's a sphere that's closer and blocking that cylinder, so we only execute the closest hit shader that's on the sphere. In contrast, we have the next ray down, which intersects with both a prism with an any hit shader on it and a cylinder with a closest hit shader on it. In this case, if we happen to intersect with the rectangular prism first, then the any hit shader executes immediately, even before we're done traversing the acceleration structure. So then when we get to the end and execute the closest hit shader, we might find out that it doesn't even use the results of that calculation, and we've just done that extra work for no reason. So you can see how any hit shaders can be more expensive than closest hit shaders, but you would still want to use them in cases like the bottom here, where the ray is intersecting with two prisms with an any hit shader, and it's collecting color data from both of them in order to do a simple alpha blend transparency. So here's how that fits into Unity. You save your raygen and miss shaders in a .raytrace file, like I mentioned earlier, and then that gets imported into Unity as this new ray tracing shader class that we've added in 19.3. Then the order of operations for dispatching that shader go as follows. And this is all done in C# in your script that you write. First, you specify the pass name that you're using for this dispatch. This pass name needs to match between the dispatch and the surface shaders that you're targeting with this dispatch. So in your surface shader, you'll have your closest hit shaders, and as you'll see later, it has a pass name that needs to match the pass name you're setting here. Then you need to bind the acceleration structure you're tracing against and any other properties like your typical shader properties, textures, matrices, etc. Finally, you can call dispatch rays for a given dispatch width, height, and depth. And the bindings that I've given here are all for the command buffer, and they're the bindings that are used in the scriptable render pipeline. But if you want to do immediate execution instead, then there are analogous bindings available from the ray tracing shader class itself. So here's a basic example of a ray generation shader. In red, we have DXR specific features and intrinsics, and in blue, we have your normal shader properties that are declared and bound elsewhere exactly as you would in your typical shader. So firstly, you have to declare what kind of shader you're authoring. In this case, we're writing a ray generation shader. And then you have to populate a ray description and a ray payload. In this case, we're using some DXR intrinsics to populate that ray description and payload. And then you call trace ray on that ray description and payload, and this is what actually casts your ray into that acceleration structure. In the same .raytrace shader, you usually also see a miss shader. So you notice in this case that the shader type is declared as miss, and it has this SV ray payload semantic, which is a DXR feature that's available to all shaders that are executed as a result of a trace ray call. So ray payload is actually a completely user-defined struct. So usually you'd have color in it, just as an example. But of course, the more stuff you shove into your ray payload, the more expensive it is to cast that ray. This mist shader is simply using world ray direction in order to sample a skybox texture and return that color, or add that color to the payload, rather. So if you want to learn more about DXR semantics and intrinsics, I've linked the slides to Chris Wyman's Intro to DXR talk, and that has several tables with those intrinsics and what they do. So as for surface shaders, here's an example of a Unity shader that has both a path for rasterization and a path for ray tracing. You'll notice that the ray tracing shader, again, has that path name that I keep on mentioning. It also has to be written in HLSL, and it has to define a pragma for ray tracing. This shader also has an SV intersection attributes semantic in addition to the ray payload semantic. And attribute data is, once again, entirely user-defined, but it usually has a float 2 for barycentrics, which is just a way of representing where in a triangle your intersection is located in terms of distance to each of the vertices in the triangle. This hit shader does the exact same thing as the surface shader above it, where it just like colors the object a flat color based on the albedo. Okay, so now that you have some background, here's what you need to get started with Unity DirectX ray tracing. You need Windows 10 version 1809 or greater. You need Unity 2019.3b1 or greater. And you need a graphics card that supports RTX. So RTX isn't technically vendor specific, and because of that, DXR isn't technically vendor specific, and because of that, our implementation isn't vendor specific. It just happens that currently only NVIDIA graphics cards support DXR or RTX. Anyways, once you have the hardware and software set up, you go into your project settings and then make sure DirectX 12 is selected as your Windows graphics API. Next, for the high definition render pipeline, you have a few more steps. So the major thing is you have to clone HDRP from GitHub, and then I'm not going to go into all the steps after that here, because it's quite a bit to read off, but the slides will be available so you can go through this offline, or you can take pictures of it right now if you want. Okay, so everything's set up and you're ready to trace rays. The API I've been talking about actually works on any graphics pipeline, but we only officially support it for HDRP, which most people will want to use anyways because it takes care of everything I just explained to you in terms of the shader authoring, shader dispatches, even denoising, and integration with existing rasterization features. And it does this all in a way that you can control those new ray tracing features through a handy UI inspector. If you're feeling adventurous, all the API I just described for dispatch ray and everything is available through C#. So you're still welcome to author your own ray tracing features from scratch using that API. I also wanted to point out a few features that we don't have supported yet. We don't have intersection shaders, we don't have animated meshes, as I mentioned earlier, and we don't have procedural geometry such as terrain yet. Okay, so now to take a closer look at how HDRP uses that API to implement ray tracing. And you can take this as an example or as inspiration for writing your own features, or just as if you want to know more about the features that you're going to be using in HDRP. So shown in green here, we have the ray traced effects supported by HDRP and roughly where they fit in the HDRP render graph. Note that this graph is extremely condensed. A bunch of the features that are in HDRP I've omitted for the sake of legibility. But for the first 6 ray tracing passes that you see on the left there, what HDRP does is it actually skips the primary ray cast, so it doesn't actually cast its rays from the camera. Instead, it takes the G buffer that it's already generated through rasterization. It computes the location of the first ray hit from the depth and normal G buffers, and then it uses that to cast secondary rays. I also want to point out the RT light clusters passed, which is something I'll go into more detail later, but it's necessary for the light calculations that are done in the reflections and in the indirect diffuse pass. Finally, the ray trace transparent pass takes place after all the opaque rendering has already finished, but is done before post-processing. So there are three main buckets of ray traced effects in HDRP: indirect lighting, shadows, and transparence. So both indirect diffuse and indirect specular, also known as global illumination and reflections, do multiple bounces of ray casts. And in order to get that running at speed, those samples are accumulated over a number of previous frames. The big difference between indirect diffuse and indirect specular is in the probability distribution function that they sample in order to compute the directions of those ray bounces. So for indirect diffuse, they just sample a Lambert lobe, and for indirect specular, they sample an isotropic GGX lobe. In addition, the indirect specular lighting calculations are done with a split sum approximation so that we can pre-compute some of that math and get it performing a little bit faster. And I also mentioned ambient occlusion here, even though it's not technically lighting, because it uses the exact same algorithm as global illumination does, but just with one bounce and no color calculations. So those familiar with HDRP might be familiar with tile-based lighting. This cluster-based light list stuff that they do is just tile-based lighting, but in 3D. So what happens is you break up the 3D space of your scene into a number of voxels, and each of those voxels is associated with a list of lights that are in range to affect that voxel. And that's illustrated on the debug view to the right there for the Cornell box, where the color of the tile represents the number of lights in the light list for that voxel. So for practical purposes, only lights within a certain 3D culling radius of the camera are tested for inclusion in these light lists. Next, we have shadows. So for directional light, the shadows are ray traced by casting rays across a disk that is used to model the sun or the source of the directional light. And the disk of that the size of that disk may be adjusted, and the two images that you see there are just on the left hand you have a slightly smaller disk size, and on the right hand you have a slightly wider disk size. For area lights, we also cast rays across the surface of the light source, but the shape is, instead of a disk, it's the shape of the actual area light. And the trick here is in combining these shadows with the analytically computed lighting, which is a lot more realistic for area lights than modeling the light as a directional light source or a point light source or anything else. For details on how that's done, you can, I've linked the paper by Eric Heitz on using a ratio estimator to combine the two, but that's outside of the scope of this talk. Finally, we have transparency. So this is the one pass where we need to cast our primary rays, and the reason for that is that in addition to hit position, we also need angle of incidence in order to calculate refraction. So on top of that first ray, each bounce also generates two additional rays, one for transmission and one for reflection. And the more overlapping transparent layers you have, the more bounces you need in order to fully render how that transparency looks. So you can see that this pass is fairly expensive, and so you should probably use it sparingly. So in order to get all these effects running at a reasonable speed, we need to get clever about sampling. Matt Farr has a fantastic talk on the subject of sampling for path tracing, but the gist is that you want to choose samples in a way that minimizes variance so that we can construct as consistent an image as possible from as few samples as possible. This is how HDRP does that. It uses the ray pixel coordinates for the given ray to sample spatial noise from a dithered blue noise texture, where blue noise is just a type of noise that's been designed to have less variance. The results of that sample is combined with the frame index in order to sample temporal noise from a looping Sobel sequence. And then the output of that is mapped to the appropriate probability distribution function for each effect, represented on the right by the blue, red, and green lobes, in order to sample a raycast direction. Of course, where we have sampling, we must have denoising. So HDRP does denoising per effect in a compute shader. Samples are gathered from up to 8 previous frames, and of course we need to do reprojection in order to correct for camera motion between the frames. Then once we've gathered all those samples, a separable bilateral Gaussian filter is used in order to denoise those samples. Now this filter uses the depth and normal geobuffers, once again, to detect and avoid artifacting or blurring across edges or corners where we really shouldn't be blurring. And because of this, this denoising is incompatible with transparent objects. Lastly, I'd like to point out a few of the knobs you can use in HDRP to tweak either towards fidelity or performance in your ray traced effects. The per effect config may be accessed through the volume inspector shown on the right. And from there, you can control ray length, where shorter rays run faster, number of samples, where fewer rays run faster, and number of bounces, where fewer bounces is faster. You can also tailor your content to improve ray tracing performance. And the big thing here is in reducing mesh count. So if you have a complex mesh with many submeshes, you want to merge together as many submeshes as possible that share the same material. You can also construct multiple acceleration structures, each with fewer total meshes, if, like, for a given ray trace effect, you only want to affect some of the meshes. Similarly, you can use layer masks to control which meshes are ray traced, and these masks are managed both per effect and per camera. And since HDRP applies these ray tracing effects through volumes, you can also be selective about which volumes have which effects based on the content contained in that volume. I'd like to acknowledge the following people for their contributions both to ray tracing at Unity and this presentation. Anis for developing the HDRP side of ray tracing pretty much entirely. Yonit for developing the engine side of ray tracing pretty much entirely. And everybody else for helping me throw together this presentation within the week before SIGGRAPH. And with that, I guess I'll mention that Unity is hiring. Graphics is the team I work on. It's the team I'm gonna champion, I guess, since it's the one I can speak for. And if you want more information about Unity in general or tutorials, here are the links. And with that, I'll open up the floor for questions. I know I didn't go into as much basics and background as I wanted to, so hopefully I can cover that now. Thank you.
You mentioned that sampling and denoising transparencies were not supported. Is there any other way to handle that scenario?
For transparents, I don't. So first of all, for transparents, the way they're rendered, there's no roughness to it. So we only have like glossy transparents at the moment. And because of that, so it turns out with ray tracing, if you're either fully glossy, if you're fully glossy, it's a lot cheaper than if you're a little bit rough. So since the transparents are fully glossy, every sample, you don't need multiple samples for each pixel, and you don't actually need denoising. So there's the limitation that we don't have rough transparency yet, but the corollary to that is we don't need to denoise our transparents. Yes. Okay, hang on. I'm realizing I didn't repeat your question. The question that I just answered was, since denoising doesn't work for transparents, are there any alternative for transparents? Sorry about that. And the question that you asked just now is whether there's any restrictions on geometry in the scene, like do meshes need to be convex? And so So I'm going to reveal at this point that I don't remember what a convex mesh is. Is it related to the ordering of the vertices around the triangle, or? Okay, so I feel like I don't personally have enough information to answer your question, and I apologize for that. I do know that there are some settings that you can set in our API, like flags that indicate the winding direction and the facing of the triangles, but if that doesn't serve your purposes, then I can't give you any information beyond that. Yes.
I know DirectX, not DirectX questions, but what do you expect to have them on the platform?
So I'm not sure what I'm allowed to say necessarily. I will say that internally there's a lot of interest in Vulkan and activity in that area. I just can't commit to any of it. Yes.
You mentioned that the denoising use information from frames, right? How do you avoid ghosting and doing stuff? Generally have a temporal algorithm.
Okay, sorry, I'm going to step back again because I'm realizing I didn't repeat your first question once again. So the first question was, when will support for platforms outside of those supported by DXR come to Unity? And this question is, oh my gosh, I forgot. Do you mind repeating?
How do you avoid temporal like
Right. Okay, so the question was, how do you, since we accumulate samples over multiple frames, how do you avoid temporal issues like ghosting and I assume instability also? So the answer is that we don't really. If you go to our demo, it looks super nice, but in particular, if you download the Office demo, that was available both for the experimental release of ray tracing and will be available for 19.3, and you pan around, you'll see some ghosting in the reflections, and we're going to continue to work on that, but it's still there. For flickering, really what we've done for that is the blue noise thing that we've adopted in order to reduce variance just in the samples themselves.
So the reflections of objects and other objects fall under the category of ray trace specular, and so with the denoising part being in there, are all reflections all blurry?
So the question was, since, so are all reflections of objects and other objects subject to denoising, and because of that, are they all a little blurry? Yes. So so I think, well, I think you can set your max roughness so that it falls back to like just glossy reflections above a certain point. But anytime you're using the ray traced reflections or the rough reflections, then it's going to be a bit blurry, even if you like dial it all the way up. And I say that based on my own experience fiddling around with the demo that we have. Even when I scaled up the glossiness all the way, it was still a bit blurry. But the thing I'm not sure about is if that's just because I didn't tweak the max glossiness cutoff for ray tracing in the volume for it. Oh, okay. All right, that's all the time I have. Thank you for listening.